everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I am super happy to have Ori Fox with us today. Hi, Ori.
How's it going? Your singing there really gets me in a good mood before the interview starts.
Oh, yeah, you're letting me know my trade secrets. So yes, I tend to sing before these start, and I just get people warmed up and make them smile, and it's all good stuff. I'm a terrible singer, by the way, people. So. Horrible. But it is May 3rd on 2022 as we record this one. And Ori, where are you located at?
Yeah, I work at the Space Telescope Science Institute in Baltimore, Maryland, now home of the JWST Mission Control, very exciting. But I live all the way down 295 in Washington, D.C. My wife gets to walk to work, so I do the commute. But really, it's not too bad. It's a reverse commute, so I'm used to it by now.
Yeah, very good. And we got springtime on the East Coast in DC area?
Yeah,
awesome.
The flowers are blooming. We're working on our garden a bit. It's actually a little chillier than I'm used to for the beginning of May. We had a nice, I don't know, it's an 80-degree day the other day, but today it's in the 50s. So
cool. What do you grow in your garden?
We're just working on flowers and things like that. Working on our tulips. Actually, we had all these tulips, but we put them in this year for the first time, and they don't seem to be coming up. So we're trying to figure out what's going on.
Maybe they're just late.
Yeah.
I have grapes. I have a wall of grapes. We planted them about 6 years ago, and so they're going gangbusters this year. I'm going to get all kinds of grapes this year.
Very nice.
Maybe I'll have to learn how to make wine or something, but
I think so.
I'm gonna have a lot of grapes this year. That is an awesome piece of artwork over your right shoulder. My eye keeps going to it. So
yes.
What is that?
Yes, this is my little collector's wall. I'm a collector at heart. All sorts of different things, bobbleheads, baseballs, souvenir coins. But this painting's really nice. One of my childhood friends' mothers is actually an artist, and she just paints whatever inspires her. And she knows I'm in the sciences, but she doesn't actually know what I do. And she showed me her painting a couple years ago that was inspired by the gravitational wave signature.
Yeah.
And you might be able to see there's a neutron star right in the center, and the gravitational waves emitting outward. It's a bit abstract. And she said, "Do you like it?" I said, and I was involved with those follow-up observations, and she had no idea. And I told her the whole story and all about it and how exciting it was. And she said, I'm free to have it. I think this thing normally can retail for around $2,000 or $3,000. So it was pretty nice. Her name's Madeline Bobley.
So there you go. There's a shout out.
Look, there's a plug. Yeah.
Very cool. Very cool. Very nice. Ori, speaking of that painting, what do you like to do for research?
Well, yeah, I'm in transient astronomy. The changing sky at night. It's always doing something new, something to discover. The field is changing rapidly. It is transient in nature. There are a number of really exciting things coming online, surveys. We have, of course, Rubin LSST. We have Roman coming up in a few years. JWST will hopefully unveil a whole new type of supernova in the high redshift universe from POP3 stars. So the field is still changing very quickly. And the fact is, we know that, massive stars explode, but you might be surprised by how little we know about which types of stars explode as which type of explosions and how. Right. And that's really the name of the game, is understanding the underlying physics and stellar evolution.
Cool. Very cool. And that is going to bring us to this most awesome APJ letter. Open access, people. You can go get it for free. Go grab it. The candidate progenitor companion star of the type 1BC SN 2013 GE. And Ori, take us away.
Okay. So, I want to start off by talking about the title for a second. It's It's a bit muted in my opinion, but the co-op, that's important in science because you don't want to oversell the science. I think that's a general rule of thumb.
Yep.
And this is a candidate progenitor companion. It may not be the actual progenitor companion. We do need to do follow-up observations, but we're pretty sure that this is the companion star to a Type 1b supernova 2013 GE specifically. In which case, and so this is, if you don't listen to the whole podcast and you just want to have one takeaway, this is the first detection of a companion star that survived an explosion of a stripped envelope supernova.
There we go.
And that's pretty big news. And I'm gonna try to really underscore why that's big news throughout this paper, and I hope to get that message across. So that's what I want you to stay for and listen to.
Cool.
And of course, a lot of this work was not done on my own. I have great collaborators all listed right there from around the world. We have theorists, we have observers, we have grad students and postdocs and senior scientists. So it's really an extraordinary team. We've been working on this for probably over a decade now. And I'm going to tell you a little bit about the history as we move into the introduction.
Cool.
So yeah, let's scroll down and I guess get started with the introduction.
Okay.
So the history here is understanding, like I said, a little bit about what types of stars explode as which types of supernovae. Mm-hmm. And this is trying to, fit into the broader question that all astronomers, I think, ask. I think this is really the big question in astronomy. This is the goal. How do stars get born? How do they die? Mm-hmm. And how did our sun form? How did our solar system form? How did life come to be? And so that's what we want to know. Where did we come from? Where are we going? It's sort of the big picture, a little bit philosophical, but to answer that question, we have to really get into the detailed science. And stellar evolution remains, I think, quite an open field. We understand single stars quite a bit, but we don't necessarily understand more complex systems. And those are increasingly more and more important. The first clues about this really came from supernova explosions, where we see that there are some types of supernovae called stripped envelope supernovae, where the outer envelopes are completely stripped before the time of the explosion. Okay. You can think of a star like an onion model. We often use that analogy where you have all sorts of different elements from iron all the way out to hydrogen, heavier and heavier elements as you get closer into the core. Mm-hmm. And we know that some supernovae, when they explode, do not show any hydrogen or helium in their spectra. And why this occurs has been a question since supernovae were beginning to get studied back in the early 1900s.
Zwicky.
Exactly. We have these famous stories of Zwicky going out there, and he had two different types of supernovae, one with hydrogen, one without. Exactly. And he was finding what, on average, a couple supernovae per year. Now we're finding, a couple of supernovae per hour, right? It's just incredible how that field has changed.
I wish to formally lodge my complaint with the numbering system, right? So 4 or 5 letters out here.
It's in 2013, you were still able to handle the 2 letters, but in 2022, it's getting a little out of control.
Yeah, it's getting out of hand. Okay.
Yeah. So, we going into the 1930s and 1940s was the discovery of the Hertzsprung-Russell diagram, mm-hmm. which is nicknamed the HR diagram, where we know that there's this relationship between a star's mass and a star's luminosity, mm-hmm. and temperature as well. And so by the turn of the century, by about 2000, theorists were starting to conclude that, well, the stripping of the outer envelope must be occurring because you have brighter, more massive stars with stronger stellar winds that are able to remove that outer envelope before the star explodes.
Okay.
This made a lot of sense. The theory looked really good. And then HST started getting observations. Hubble was launched in 1992. You had a couple years before the corrective lenses were placed. And, it took about a decade before there were a substantial number of archival observations of nearby galaxies for ancillary science. But what the community started to notice was, amongst many other things, but in the pre-explosion images of these nearby galaxies where these stripped envelope supernovae were occurring, there was no evidence for really bright, luminous, massive stars.
Okay.
Now, we were seeing bright stars for the lower mass supernovae like type 2Ps, but not for these stripped envelope events. So there was this push to say, well, maybe massive stars are not actually the progenitors to these stripped envelope supernovae. Now, that has an impact on everything that we understand about stellar evolution, including the initial mass function of stars, stellar winds, feedback into galaxies, dust production, metallicity evolution, yada, 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 right? So it depends on whether these massive stars are exploding as stripped envelope supernovae or not. Stripped envelope supernovae comprise 25% of all core collapse supernova events.
Okay.
So the community really started to consider other possibilities. And of course, binary stars was a very alluring answer because you might have a binary companion that's circling the star and stripping off that outer envelope of material. And the binary evolution code really took off. There's been a lot of development over the past 10 or 15 years. And it's a very comprehensive set of models.
Cool.
The problem is twofold. First of all, the models themselves rely on a lot of assumptions because we don't actually know a lot of the observational details about the initial and final states of a binary evolution star system, okay? We also don't know necessarily observationally all the details about the interaction and the mass transfer physics of the gas itself. There are a lot of assumptions that go into play. The other point is that we have not actually confirmed that binary stars are doing the stripping from an observational perspective. To do that, you need to go to the supernova location years after the supernova exploded and faded and look for a surviving companion. And to do that, you need to look with HST because that's the only way you can get the necessary resolution. And you also have to look in the ultraviolet because when your primary star is stripped of that outer envelope, it goes right onto your companion star, and that companion star puffs up and it gets hotter and more luminous and bluer, and it glows in the ultraviolet. So again, you need HST for those two reasons, and those two reasons make it very difficult to follow up because stripped envelope supernovae, especially in the range and the distance range that Hubble can see, is actually a very small number. You might only get one per year at most.
Okay. Mm-hmm.
Okay. So going into 2000, let's go back a little bit to 2010. Okay. And I was a postdoc at Berkeley with Alex Filipenko. Okay. And the most tempting object to do this experiment with was not a fully stripped type 1 DC supernova, but actually a partially stripped, we call it a type 2B supernova. Uh-huh. And this was called 1993J. It was an M81 at only 3 megaparsecs. I mean, you can't get any closer than that, really. No. And we were able to go after it with a STIS spectrum with Hubble, and we were able to detect this UV continuum that was entirely consistent with a hot B star, which is what you would expect to be left over from this companion interaction. And it took nearly 20 years to observe this because 1993J had so much material around it because it was partially stripped, not fully stripped, that the shock was interacting with all this material for years, 20 years that it's glowing. In fact, you can go out and you can still see 1993J today. Yes. So it's this really incredible story. But then there weren't really too many other candidates, okay? And so nearly a decade went by while we were sort of honing our program to try to figure out how to optimize it for other targets. Okay. And we slowly started to build up a nearby sample with really high precision astrometry of the supernova itself with Hubble. Okay. That we could go back to years later after the supernova faded sufficiently. From the ground, most supernovae fade on the course of a few years, but when you're looking at it with Hubble, you have to wait a few months if you're looking at it from the ground, but with Hubble, you have to wait a few years at a minimum. So, I hope this timeline is showing you 2013 GE, which is what we're talking about today, was sort of one of the next big candidates on our list. Remember, our first study was done in 2010, and then 2013 GE came along. Mm-hmm. And we bided our time, but it wasn't until 2021 that this thing faded sufficiently for us to finally do this experiment. And so that's what we're going to talk about today is cool. 2013 GE and the follow-up. And this is an extraordinary case because it's not a partially stripped, it's a fully stripped envelope supernova. Okay. So I hope that set the story. And now we're going to go, the observations are relatively straightforward. We followed this thing. What we're going to look at is how we followed this thing at V-band in the F555W filter for a number of years, watching it decline. Mm-hmm. And we wanted to make sure that it was declined sufficiently in the optical that we didn't have to worry about any contributions in the UV. Okay. Because the last thing we want to do is make the claim that we found the supernova companion that survived the explosion, but that we weren't looking at the supernova, but that we ended up looking at the supernova itself. So we waited for a good 7 years, and then we got UV and optical photometry so that we could put together a spectral energy distribution to try to understand the shape of the star's spectrum, even though we weren't able to get a spectrum itself. So remember, 93J was at 3 megaparsecs. Mm-hmm. This is at about 20 megaparsecs. So you can see that we didn't have a lot of options in between. We had to go from 3 to 20 megaparsecs, mm-hmm. and that's really pushing the envelope of HST sensitivity. We couldn't get a spectrum. We had to do photometry. Mm. Okay. And of course, a big part of this, we talk about the distance and reddening. When you get your photometry and you put it onto a color magnitude diagram, which we'll do at the end here, mm-hmm. it's critical that how far away this thing is and how much reddening you have, or else you're going to get values that don't make a lot of sense. Right. And believe it or not, distance is such an important part of astronomy, but it's still a bit of an art depending on which technique you use. And there's a number of different distance measurements out there for the host galaxy, right? Which is NGC 3287, a beautiful galaxy. If I have time at the end, maybe I'll share a couple pictures with you. It's just a spectacular galaxy. Cool. Okay, so let's scroll down, and we've been looking at a lot of text. Let's get into a couple pictures, right? And so there are our observations. You can keep scrolling. Here we go. Okay. Let's get to a picture at long last. Okay, so here is an image with the Hubble in the V-band filter, like I mentioned. In the upper left, you have your 2016 image. And in the 2013 image, the thing was saturating the entire detector. You couldn't even look at anything. Mm-hmm. This was 2016 years later. You can see that there's sort of this smudge off to the right. We call that source B. Yeah. It's probably a nearby star forming region, probably a collection of stars. It's not an isolated point source. But you can see the supernova itself fades over time. Yeah. So you can look at 2016, 2019, and then all the way at the bottom is 2020. And you can see that there's practically nothing even there in the f/5.5 filter anymore.
Right.
And it was 2020 when we said, okay, now it's sufficiently faded that we feel confident that anything we look at in the UV filters is going to be a surviving companion if we detect it, because the shape of a supernova spectrum does not get brighter in the UV 8 years after the explosion. At that point, you're very red, cold, well, not cold, cool. Your spectrum is shifted all the way out to longer wavelengths. So anything you detect in the UV is not the supernova, okay? So I want to make that clear.
Yes.
And you can see that there's a very nice, clear detection in the F275 and the F336 filters. Those refer to about, those are the two UV filters on Hubble's WIFC-3, Wide Field Camera 3. They cover about 2,000 and 3,000 angstroms respectively. As you go out to longer wavelengths, the F438 and then the F555, of course, there's almost nothing, because of course you expect that if your spectrum probably has some sort of slope where you're brightest in the UV. And we're going to look at what that spectrum looks like next.
Cool.
Okay, so this was great news. We got these data and we said, wow, we got a detection. I should point out that, we had been doing this for a while. We have a couple other cases where all we have are upper limits. Okay, so this wasn't the first time we tried this, but it was the first time we had a successful detection. So that's an important caveat. Okay, so scroll down. Okay. And so, yeah, we'll talk about these two figures. So the upper figure is our V-band light curve, and the number of points all the way on the left are the early time light curve that had been observed by a number of ground-based telescopes. It was, it's really bright, apparent magnitude of about 15. And the last 3 data points are the Hubble observations that we just looked at.
Yes.
And you can see that V-band is steadily declining. And the V-band decline is not consistent with the radioactive decay, which means that there probably was some other source of energy going on. Usually that corresponds to something like circumstellar interaction. But again, it dropped, several magnitudes, and there's probably still a little bit of residual contribution from that nearby source, especially in the V-band. So this is just to show that, there may be some circumstellar interaction contribution. But what we talk about in the text is that even if there is CSM interaction and shocks, you still will not get the shape of the spectrum that we're about to look at. Okay, so we can scroll down.
Ta-da.
Okay, so this is one of the, I mean, this is a letter, so it's a short paper because I think there's still a lot of outstanding questions and follow-up observations, but we wanted to get this out because the data are public. And this is probably one of the 2 key figures.
Yep.
And what you're looking at here, the first thing to look at is the black photometry points.
Okay.
Or sorry, the red photometry points, I'm sorry, which are the measurements that we made from the Hubble observations themselves in 2020. I talked about the F275, F336, F438, and F555. And what we wanted to do is we wanted to understand what sort of shape this spectrum corresponds to.
Wow.
And to do that, you want to take spectra that we know and try to fit it to the data points. And to fit a spectrum to the data points, you can convolve it with the Hubble filters and create synthetic photometry. And the synthetic photometry we show with the black circles. And I'll show you that's just the synthetic photometry that we have from our best fit. We have a lot of different types of models that we included. And in all of these cases, we assumed for the various models, we had to scale it to, some magnitude. So you can take a star spectrum, but you have to scale it to the right distance. And you have to know exactly how bright it is. And even if we know a stellar type, we don't always know the exact absolute magnitude for that star. So instead, we just scaled it to our observed apparent magnitude here, which is that's why all of these spectra cross at the exact same point, which is, about 25th magnitude in F275. And I'll tell you why it's okay to do the scaling once we get to our next image. But for now, let's just assume that it's not a problem.
Okay.
And what you're looking at are stellar models from a stellar library for all different types of stars that you might expect to see as a surviving companion to a stripped envelope supernovae. And this comes from the literature. I told you that the stellar evolution models for binary evolution are relatively advanced. And so you might end up with a number of different endpoints. And this is really a good chance to take a pause and say that the endpoint matters, because ultimately what you want to do is build up a statistical function of all the different endpoints in stripped envelope supernovae, including non-detections, where you might have just a single star, for example. Because not in some cases we do predict that single stars might be contributors, at least in some fraction of cases.
Yes.
And this binary fraction, or the distribution of stellar endpoints, will ultimately constrain all of the different binary models that are currently out there and the underlying physics. And we'll talk a little bit about that more at the end and the direction of the field.
Cool.
But in any case, what we did was we fit a number of different stars here. We don't need to get too hung up in the details right now about what the different stellar types are. We'll talk a little bit about that more in our next figure. But the resulting best fit from a chi-squared perspective is this B5 supergiant model. Now the B, if you don't know your stellar types, I don't know the exact target audience here, but you have O, B, A are your top three stars, O being the brightest, B being the next brightest, and A being the next brightest. And these all have numbers associated with them. And so the less bright you are, the lower the number, the brighter you are. And then you also have different classifications, because you have things from 1, 3, 5, and that just talks about where they are on the HR diagram, because a B star has a life and it will evolve over time, and it will turn into a puffed up supergiant towards the end of its lifetime. And so when you see a 1, that actually refers to the fact that it has evolved into its a supergiant phase. And so that's what you're looking at, is the brightness, the temperature, and where it is in its lifetime. Okay. And so our spectrum was most consistent with what we call this B5-1 model. And you can see the synthetic spectra the synthetic photometry are overplotted with those black circles. And okay, you could potentially argue that it's not perfect, but within the uncertainties, it's a pretty good fit, and that was our best chi-squared. So we're pretty happy with that.
Yeah.
If you really wanted to ask questions, you could say, well, why is that second point, the F336, so much higher than the spectrum itself? And that's just because of the way that bandpass is shaped. That's a very wide bandpass, and you have a very steep spectrum. And the way, when you convolve it, and especially where that bandpass is most sensitive, the convolved photometry for that bandpass does make that data point look a little bit higher than the spectrum itself, but it all makes sense when you look at the convolution. Okay, so let's scroll down.
Cool.
And we'll go on to the next figure.
Ooh, single star tracks. Okay, let's go there.
Yeah. Okay, so this is our final figure. Like I said, it's a letter, but ultimately the other figure was our second most. I would argue that this is probably the most important figure in the paper.
Okay.
And what we've done here is we've taken our observed photometry, which is shown with our filled circles there.
Okay.
And we've overplotted the stellar evolution tracks in these filters that are taken from the theoretical models for stars of different masses. Okay. And the two figures are actually quite similar. One is a traditional sort of HR diagram where you plot luminosity or magnitude versus temperature. The other one is more of a color magnitude diagram where you have magnitude versus color.
Yep.
But ultimately they're showing you the same thing. If you're not an expert at looking at your color magnitude diagrams, the stellar tracks begin all the way on the left-hand side. Okay, and that's what we call the main sequence. That's where stars live the majority of their life. And as they age, like I said, they go through different burning stages. They puff up, their envelopes broaden, they might get brighter. They start, when you broaden your envelope, you also get cooler, just naturally, as you might expect. And that's why you shift redward on the color magnitude diagram. You go to lower temperatures, your spectrum shifts from the UV into the, the redder parts. Yep. What we find is that all of our photometry points, I mean, this is really exciting. If you look at this plot on the left, all of the photometry points are consistent with nearly the exact same place in an evolutionary. So, you could have imagined that the blue and the green may have been, brighter or dimmer than the tracks, and the redder might have fallen right on it or something like that. But in every case, the photometry and the derived temperature from that spectrum that we looked at falls almost at the exact same location in the stellar evolutionary time sequence of that star. And so when I say evolutionary time sequence, as the star evolves off that main sequence, this is sort of a function of time going from left to right. Okay. And what we find is that the companion is quite a bit brighter than it was when it would have been on the main sequence. And it's a bit redder, even though it's still really bright in the UV, right? We saw that curve. It's a nice UV bright source. It's still redder than it would have been if it were on the main sequence. Now, this is fascinating. Okay, this is not only do we have a detection, but the location of it on the color magnitude diagram is fascinating, because the stellar evolution models predict the endpoint of the star, but in most cases, maybe 95, 98% of the cases, those stars are still on the main sequence. Relative to the main sequence, a star will survive for a very short amount of time on this track before it goes supernova, okay, itself. And so the chances of seeing it here, especially just 10 years after the explosion, are really slim. And so there are alternative hypotheses, and one is that the companion was shocked by the supernova itself when it exploded, and the shock just sort of tore through that star, and it didn't rip it apart. The analogy I like to, I'm getting ready to tweet about this, and I'm thinking about analogies, and what comes back to me are these Maxwell cassette tape commercials where the guy sitting in his chair and the music just blows his hair back, and he's blown away, but he's not blown apart, right? And the same with a Jello mold. I also found these great videos on YouTube of a Jello mold. You can disturb the Jello and it looks like it's going to fall over, but it just goes like this.
Twink, 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 twink.
Yeah.
Cool.
And it slowly comes back to equilibrium.
Sure.
And after that, it settles down. And so this could be in this like really disrupted state right now. And so this is, a really exciting prospect. We're going to look into that more as well. Yeah. Okay. So, I want to take a step back. I alluded to this at the beginning, but I think now's a good chance to sort of wrap this up and give the big picture again.
Okay.
This was a chance for the first opportunity that we've had to detect a star that survived a stripped envelope supernovae.
Yes.
Okay, there's a couple really big takeaways here.
Cool.
The first is that, well, it was the first, as far as I know, detection of such an event.
Yep.
The second is that this provides such an important constraint on understanding binary evolution models.
Yes.
Okay, we know generally how binary evolution works, but a lot of the details rely on assumptions, both of the initial state of the system, but also the final state of the system and all the physics in between. And by understanding the final state of the companion, we know the final state of the exploding star. That's been studied in depth.
Yes.
We're also able to work out from these parameters the initial states of the system. We can put together a really nice binary model, and that's going to be an upcoming paper, a really thorough, complete binary model for this particular system.
Cool. Awesome.
But that's really just the tip of the iceberg. Yeah. This is opening a whole new field, because ultimately, the different binary models that exist will create a predicted distribution of endpoints for both the primary star and the companion star. And you might imagine, if you had a completeness function, you would see something like, as you get towards 100% completeness, you would have a number of different types of parameters filled up. Namely mass, that's one of the big ones, but there's all sorts of other ones. And so what we really need is a mass distribution of endpoints for both the primary star and the secondary companion star.
That would be nice.
And to do that, we need to build up our sample. And like I said, you get at most maybe one a year. And you can only do this in the UV. And so Hubble, we don't know how many years it has left. Gyros are a limiting, factor.
Yeah.
And so we have a number of objects in our sample, but we really need those Hubble observations, and we're getting them. And we have upcoming programs, and we just put in a new proposal for that. Cool. And ultimately, we need at least a sample of maybe 10 or 12 at a minimum to at least look at this at about a 1 sigma level. When you work out the statistics, you need a sample of about a dozen. And so that's really where the field is going. Now, let me tie this in again to something that we talked about in the beginning. Kilonovae and gravitational waves. We know that these things happen from the spiraling in of a neutron star merger, or a black hole neutron star merger. The way you get a merger event or a binary system set up like that in the first place is you need two compact objects. Where do these compact object binaries come from? They come from systems just like this. Exactly like this, where you have a primary star that goes supernova. It remains in a bound system. They don't all remain bound, but if it remains in a bound system, the secondary star will then evolve over the course of, it takes a little bit longer. It's a lower mass star by nature. You know that for a fact because it was the second star to explode. Yep. The bigger they are, the faster they die. That's how it works. So you need to wait a little bit longer, not in our lifetime, but that star will ultimately explode. And then you'll have a compact object binary system, and understanding the initial states of these binary compact object systems is so important to understanding gravitational wave signatures. And so this is sort of the halfway point to getting there. Yep. And so understanding these systems better is going to be such a critical path to understanding gravitational wave events. So really this ties into so much of astronomy. And this is really just the exciting tip of the iceberg. Yeah. So I think that's a great place to leave it. And I'm happy to answer any questions, or if you want to see some pretty images, I have those as well. I don't know how you want to take it. But I really appreciate everybody's time and attention.
Sure. Well, Ori, thank you so much for walking us through this really awesome discovery paper. Maybe you were being a little shy in the title, but I won't be. It's a discovery of a companion, people. Slap, slap, slap. Yeah, you said you have a couple of really cool images of the galaxy as it goes. So why don't we go ahead and share those so you can share.
Let me do that
on NGC 20.
All right, are you able to see?
I am, and it looks very, oh, that's nice.
Okay, so this is coming from our upcoming press release. I don't think you're going to publish this in the next day, so I think we're okay for you to show this afterwards.
Yes, I will.
Great. And this is a picture of the beautiful galaxy NGC 3287. It's just such a spectacular galaxy, and you can see a zoom in of just how faint and fuzzy this supernova is. It's really just in this isolated part of the galaxy, and these are the images that we looked at in the paper. That's the fading supernova over time to the point where it just disappears in the V band. And this is, I think, a really cool artist illustration of what I was trying to convey, where you have this companion star that's sitting right next to the primary star, and it has siphoned off all of that material. And when the supernova, the stripped envelope supernova explodes, it just blows that star away, and it totally disrupts that outer envelope, and that really puffs it up. And so if you want to see an artist, a bit of the scenario, here it is. You have this star that siphons off its material. The star explodes.
Yep.
And then you have this puffed up companion star that's pretty hot. It's a little redder than you would expect for the main sequence. And then that star explodes too. And then you have these compact object binary systems that will eventually spiral inward and create some gravitational waves.
Very cool.
So, I just wanted to share that to really bring some of what we talked about today to life.
So we'll put a link below the video to the press release. That's going to be that Space Telescope putting that out.
Yes.
We'll do that. That is so awesome. Very cool. You touched on a little bit. I'm sure there's going to be a fair amount of activity. So you touched on some new modeling efforts that are coming out on this specific one. Have you pushed for telescope time on like JWST coming up to revisit this object, or where do we go over the next, let's say, 2 to 5 years on this object, or others like it?
Great question. It's really unfortunate that James Webb, which I am an instrument scientist on, is not much use to this project. Because, like I mentioned, these stars tend to be really bright in the UV, not the infrared. That slope goes so steep that by the time you get to the infrared, even JWST can't see much. Believe me, I'm brainstorming on ways to get around that. And I might have some, but not yet. But where's this going to go in the next 2 to 5 years? Well, first of all, we need more objects, that's for sure. The second thing is we need follow-up observations for this particular object. I touched on it. You could see that the source was still fading in the optical. We looked at that light curve in the F555. There might be some circumstellar interaction at play. The number one thing we need to do to confirm that this is real, which I think it is, by the way, but you have to confirm it, you have to cover all your bases, is we need another spectrum a couple years later, or another set of photometry, to show that even if the optical is continuing to fade a little bit, that the UV is static. And if the UV stays constant, we know that there's a constant source there. The other thing we need to do is we need to search through the archive of real spectra, because remember I mentioned that this supernova, or this companion star, was evolved off of the main sequence. It turns out that when you get a stellar library, all of your stars are on the main sequence. It's very hard to model spectra, or there's not a lot of effort, I guess I should say.
That's a better way to say it,
in modeling spectra that are evolved, because there's so many different evolutionary points. A lot of the detailed physics still is, a little bit ambiguous. And so to model those spectra is very difficult. So our stellar matches were main sequence stars, not evolved stars, and that might help explain why our synthetic photometry didn't match up perfectly to the observed photometry. So we have to go find stars that are evolved off that main sequence just a bit, and then see how those match up. We also need to look into, if this is a constant source, we also have to rule out the potential for an underlying UV source from like a galaxy cluster.
Or something.
And yeah, and that should be relatively easy to do. We need to look at, there's a number of photometry for different stellar clusters out there. We just need to compare our colors to their colors. And the other groups have done this. It's a relatively straightforward thing. We just did not have time for it in this letter. And your goal is to show that the colors of your source are offset from the typical colors of clusters.
Okay.
And once we do those three things, we should be able to, put the nail in the coffin here and say this is definitely the companion star.
I have a question about the supernova. You showed a radioactive curve. Do we have an estimate of the nickel 56 mass from the supernova itself?
Yeah, that's a great question. We do, but I don't actually remember it. I have to go back to the original discovery paper and look at what they modeled. So I was not part of the original discovery paper. That was led by one of my collaborators, Maria Drought.
Oh yeah.
And she does a really beautiful analysis of that light curve.
Yeah.
It's probably a good time to bring up something interesting about that light curve. The light curve in the original discovery paper actually has two peaks, okay? And most supernovae do not have two peaks. You get brighter, then you dim.
You dim.
There are some models out there that argue that depending on your different cooling curves for different parts of your supernova, you might actually see one part get hot first and then the other part due to like shock breakout and things like that. And so you could potentially have two peaks, but there's a lot of ambiguity around those models. And we don't see that in every stripped envelope supernova. So there was another hypothesis put forward in that paper. It was not the leading hypothesis. I can't stress that enough, but it suggested that the second peak might actually be the shock ramming into the companion star, if a companion star existed.
The companion, okay, well.
And so you start fading, and then the shock hits the companion, and everything gets bright again. Now, people have been searching for signatures like this in all different types of supernovae, and there's a lot of success out there. We don't know if that's the case here, but now that we've discovered this surviving companion, there's a very good, it gives more credibility to that hypothesis. Let's put it that way. So that's a pretty interesting little nugget.
It's less far out. That's very awesome. Very cool. So this is going to be a really cool field over the next couple of years. I'm really looking forward to, in particular this object, but also, potential discoveries of other ones as we work toward that 1 sigma statistical limit. So it'd be very cool.
It's still 1 sigma. I mean, hey, we want to get to 3 sigmas. So, we'll see how long Hubble's up there or how, generous the pack is,
Yeah, or I'll wish you a new UV satellite.
Well, that's true. I should be able to survive till the next UV satellite, Louvoir or whatever it ends up being. Yeah. So
awesome. Ori, thank you so much for again walking us through your very lovely discovery article. Appreciate it.
Thank you. Thanks for having me.
Yeah, and that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we will see you on the next one. Bye-bye.